First of all, apologies for the delay. I hope you all enjoyed the break you had last week. Gave you extra time to work on the first homework. So we're going to pick it up where we're not last time. We have about 5 slides left to go on what I was hoping we would cover last time. So we'll finish it up. And then we'll start with some new material. We posted the new set of slides this morning on the web. So maybe, hopefully, some of you had a chance to get them. I'll try to post them earlier next time, but I totally forgot. So I just posted them this morning. So let's refresh our minds a little bit what we saw last time. So it's been 2 weeks. Let's see. We talked for a while about antennas. And remember that we talked about something called the radiation pattern that characterizes the ability of an antenna to concentrate power in certain directions at the expense of others. We saw some of the shapes for typical antennas that are used in wireless systems, especially for sectorized antennas and for terminal antennas. We saw that the gain is the largest value of the pattern in the direction of maximum energy concentration. We talked a bit about polarization, which determines the orientation of the fields as they travel in space. And it's a characteristic of electromagnetic waves that will be interesting to us a little later. So we just introduced the notion. Then we saw that the exact solution of Maxwell's equations, which is what will be required to predict exactly how the waves propagate from the transmitter to the receiver, is unsolvable because of computational limitations and because of the fact that we cannot model exactly the environment. So we saw a number of approximate techniques, especially different versions of ray tracing, that are sometimes used for controlled environments, especially for indoor environments, where you can model the place, the size of the rooms, the walls, the furniture, etc., and try to approximate the solution of the Maxwell equations by launching rays. And we saw that even this method that is only approximate, it's quite complex, and it's only so accurate. Then we saw that as a result, the general approach is to resort to statistical modeling, where we regard the channel as a stochastic quantity, as random. And so we use a number of parameters to tune these stochastic properties to the actual measurements that are made in the field. So we made a very important distinction between what we call large-scale features, which takes place over relatively long distances on the order of at least a few meters, sometimes hundreds of meters and kilometers. And then there's what we call small-scale features, which happen within distances that are on the order of the wavelength, so typically on the order of a few centimeters, maybe a few tens of centimeters at most. And we spent most of the lecture going over the 2 most important large-scale features, which are the path loss, which is deterministic, so it characterizes the decay of power with distance because of the fact that the energy is expanding in all directions. So in a particular direction, the energy goes down with distance. That's the path loss. And then we saw something that we call shadow fading, which is stochastic, and which adds on top of the path loss. These shadow fading has to do with blockage, especially. So with obstacles that are in the way of the propagation paths. Then we went over a number of path loss models. So the simplest one we saw was the line of sight model, which is it's an idealization where the receiver and the transmitter are in free space. There's nothing else in the universe, and so the wave just goes from one to the other in a straight line. We saw that has a very simple behavior that's given by the Friis formula. And we saw we used the two-ray model to account for the presence of the ground, and we saw that makes a huge difference. We saw that as opposed to following with the square of the distance, when we account for the presence of the ground and we're sufficiently far, the path loss shows a decay that's with the 4th power of the distance. So that's a very significant difference that's due simply to the presence of the ground. Then we saw some empirical models, remember, the Okumura and the Hata models, especially, that are based on measurements made in Tokyo, most of them. And so people build models that try to match the behaviors that are exhibited by these measurements. And then we saw the simplified model, which is by far the most popular one, which has an intercept point at some distance z0, and then it has a decay with some exponent gamma. Okay. So as I already said, we saw that the power falls off with the square of the distance into space, or with the fourth power of the distance in a two-path model, which evidences the crucial role of the ground reflection. The simplified model, as I just told you, is simply given by this k times d0 over d to the gamma. So k is the intercept at distance d0, and gamma is the exponent. As I already said, the random attenuation due to shadow fading can be modeled typically as an normal random variable. And we saw that there is a plausible explanation of why it's not normal that comes from the Central-Limit theorem. So we have that the product of the blockages expressed in decibels adds up. The product becomes a summation. And so if you have a sufficient large number of obstacles, this sum is going to give us something that looks pretty much Gaussian in the dB domain. So that's why it's not normal. That's a somewhat fishy interpretation because usually you don't have so many obstacles. But it is a fact that measurements time over and over again indicate that the shadow fading is not normal. So that's a very, in fact, it's pretty much the only model used for shadow fading. We saw that the shadow fading correlates over distances that have to do with the size of the obstacles. That could be like the size of the building or size of a small hill. So typically it will be on the order of tens of meters, maybe 100 meters, no more than that. And that's how we finish the lecture. So we're now going to cover these 2 points, and we'll wrap up this part and move on to the next material, which corresponds with chapter 3 of the textbook. So let me backtrack. All right, so let's start with this new stuff. We're going to introduce now the notion of outage probability. This is a very important concept and one that we'll be seeing throughout the course in other areas as well, so you'll get to be familiar with it. This is the first time we see it. Let's imagine for a second that we have only path loss, so that there is no shadow fading. So everything is deterministic. The more far away you go, the less power you receive. And so the coverage areas will be circular, right? So if you define as coverage area the area of which the power is constant, perceived power is constant, it's going to be circles. So the more far away you go, the bigger the circle, the smaller the power. But the coverage areas will be circular, just by symmetry, right? I'm assuming here that the antenna itself is omnidirectional. Now, unfortunately, we never had this situation. We always have path loss and shadow fading. So then we find what Professor Goldsmith calls in the book amoeba cells. So we have irregular shapes for the coverage areas, right? So if you plot a contour of an area on whose boundary the receive power is constant, it's going to have some strange shape, right? Depending on the obstacle. For example, here we may have some like building or something that's blocking this part, and so that part actually has bad coverage, even though it's inside the circle. So we'll define the outage probability at some point. Let's pick a certain point which is a distance d from the transmitter. So the outage probability at distance d will be the probability that the received power is below some minimum. Let's call it P min, which is what the system needs for acceptable performance. Okay, and that's actually how systems work. So your cell phone needs a minimum amount of power. That's called the sensitivity of the cell phone. So better cell phones have better sensitivity. That's the minimum it needs to acquire the signal. So if the signal is weaker than that, it's not going to pick it up. And in fact, different brands of cell phones have different sensitivities. Typically, like a cheap phone will have a bad sensitivity, and a more expensive phone will have a better sensitivity. So you're paying for something. So it may well happen that you can have a phone and somebody else will be next to you, and your phone may work and their phone doesn't work because it has a better sensitivity. A few dB better can make all the difference, right? So let's say P min is the minimum we need for a good performance. So the outage probability is the probability that at distance d, the received power is less than this minimum. Okay, so that's going to be the outage probability. Let's call it P out at distance d for a minimum power P min. Okay, so how can we compute this? Well, it's pretty easy actually, because the log normal shadow fading, the shadow fading is log normal, right? So if we express everything in dB, as you can see, everything here is in dB, right? Then we have a Gaussian variable, right? So the received power is the Gaussian random variable whose mean is the path loss and whose Gaussianity is defined by the shadow fading. Okay? So remember we introduced something called the Gaussian Q function, which gives us the probability that the value of a Gaussian random variable is above a certain level. Okay? So here we want the probability that the Gaussian random variable is below a certain level. So instead of a Q function, we'll have a 1 minus Q. Okay? We have the complementary function, which gives us the probability that something is below a certain threshold. Okay? And this Q function is evaluated at P min in dB minus the expected value of the received power, which is exactly this. If you remember the received power, using the simplified model, the received power is the transmit power times K times D0 over D. Can you guys see this? Because these boards have been used so many times, but they don't erase it. I hope you can see that. So it's pt times K times D0 over D to the gamma. So in dB, right, this is PR in dB is equal to pt in dB plus K in dB, right? Products become summations in dB plus gamma times D0 over D. Remember that when you take a logarithm, the exponent comes down. Okay, and here I think that the reason that the sign is negative is because we flip the 0 and the D. Okay, so if you flip these two guys, then the exponent becomes negative. So that's why. So this is the average. See, this is the path loss, which is the average of the shadow fading. And this sigma is the standard deviation. Okay? So this 1 minus Q gives us the probability that the received power is below P min. Okay? And remember that the expression for Q is here. It's also in the textbook. Okay? Standard function, like programs like MATLAB, for example, will give you a few functions and a lot of mathematical problems. Or you can find them on the web, tabulated. Okay? Any questions so far? Yes. Can you? This is the right. This is the path loss. So the received power is the transmit power going through the path loss and through the shadow fading, right? I don't understand the question. Which expectation? The mean. That's the mean. That's the mean, which is the path loss, exactly. Yeah, and this is the expected value. This is the path loss. Remember that the path loss is expected value. So the received signal. That's just the mean. Yeah. This is so the path loss, the shadow fading is not here yet. This is just the path loss. This is the path loss, right? Using the simplified model. This is the path loss. The path loss is actually the ratio between these two guys. Okay, so it's K times this. And then on top of that, there is shadow fading, which is Gaussian in dB. Somebody else have a question? No? Yes. Which one? Okay, let me repeat the question for the CBN students. So the question is, why isn't D naught chosen? The D naught is here, right? Yeah, typically D naught will be given to you. So the way you build the model is you're going to measure. So you're going to measure K at D naught, right? So typically, like in the homework sets, they'll tell you K and D naught. If you want to build a model from measurements, what you do is you'll make a measurement at D naught. Typically, this will be a few meters. I don't know, 10 meters. So you make a measurement at 10 meters, and the path loss at 10 meters will be exactly K. So these two are always related. In other words, K happens to be the path loss at D naught. So you can measure it, right? And then if you measure how it decays with distance, you have the exponent gamma, and that gives you the whole model. Any other questions? Are you following or are you still unsure? Okay, if you want, come at the break and we'll talk it over. Any more questions on this? Okay, so let's proceed. So we have that the outage probability at distance d, given the minimum power Pmin, is given by this 1 minus q function. And it depends on Pmin, and it depends on the path loss and on the standard deviation of the shadow fading. Okay, so actually let's go through a quick example. Maybe that will help. So let's suppose we want to find the outage probability at 150 meters. So D is 150, with the transmit power being 10 milliwatts. And we need a requirement of minus 100 and a half dBm. That's the sensitivity. And gamma is 3.71. And here you can see, for example, then give you the intercept is minus 31.54 dB at 1 meter. That's probably taken from one of the models. All right. And shadow fading has a deviation of 3.65 dB. So, in fact, here you have all the information. You just have to plug these numbers. So, 10 milliwatts is 10 dBm. So, you can put here 10 dBm. Sorry, that goes here. Here we put minus 100.5. Here we put the K in dB. Here we put the ratio to distances. One is just 1 meter, right? Yeah, so D0 is just 1, so it disappears. And D is 150 minus gamma. You just work it out. You compute the Q function from the web or from any of the math problems. And it comes down to 1.2% outage probability. So the point of this exercise is to get you a feeling for which are typical values of outage probability. So typical targets in a cellular system are between 1 and 3% are typical values for blocking. So blockage is higher than 3% are typically, or let's say coverage outages bigger than 3% are typically deemed bad service. Better than 1% is very good service. So different providers have different outage probabilities. For example, in this area, Verizon has the best coverage. And it's not only the marketing they have in TV, it's actually true, they have the best coverage. And because they spend more money. And so they target a more aggressive outage probability. The system is more expensive, but the customers are more happy. Because of the shape of the Gaussian distribution, as the outage probability diminishes, it becomes harder and harder to make it even smaller, right? So maybe we can draw this. So you have a Gaussian. So this would be in dB, right? The shadow fading. So as you want to push this into the tail, right, and make the outage probability smaller and smaller, this curve never touches 0. So you can never get 100% coverage. You can never get 0% outage. And in fact, because this becomes very flat, it's harder and harder to push it between 1%, 0.5%, etc. Okay. So in fact, it is not possible to guarantee 0 outages when you have true log normal shadow fading. Yes?
Just had a question. You said normally the outage probability is bigger than the PV, the blocking probability?
Well, they're related, yeah. The question is if the outage probability is bigger than the blocking probability or smaller. Outage has to do with coverage. So you cannot be blocked if you're out of coverage, right? Now, you could be blocked even though you're in coverage because of capacity, right? So the probability of blocking is always bigger than the outage probability because it can only be worse, right? So you have to be both in coverage and find an available channel to get service, right? So, but typically they're going to be very similar because most of the time you want to find the channel. So typically, if you are not in outage, you'll be able to make a phone call. Yeah, it's just a little higher, maybe a fraction of a percent higher than the outage probability. So they're very close. It's a very good question. Okay, so that's the outage at some distance d. Okay, now we're going to get into a more general notion. So I want to make sure that everybody understands this, because we're going to build on this now to get a more general result. So any doubts here? Is the concept clear about it? Okay, let's move on. You guys are welcome to ask questions anytime you want. Okay, so now we'll talk about cell outages, which is a somewhat more general concept, okay? So let's go back to our idealization. Let's imagine for a second that we only have path nodes. There's no shadow fading, so things are very easy. We have circles of coverage, okay? And let's imagine that, well, let's call PR with the bar on the top, the power received on the circle, okay? So if there's no shadow fading, and the minimum power we need, the sensitivity is P min, the design is very easy, right? We just choose the transmit power PT such that this PR bar is equal to P min. And so everybody's happy, right? Because inside the circle, everybody has at least P min. In fact, the guys on the boundary will have P min, the guys inside will have more than P min. So everybody's happy. So if there's no shadow fading, the design is very easy. Now, let's put back the shadow fading, and we go back into this amoeba cell with irregular contours. Okay. Now we have to choose the transmit power, and now we have a bigger problem, right? Because no matter how big the transmit power, we're going to have some places in outage, right? So we're going to choose the transmit power such that the received power on a circle equals this PR bar. But even if this PR bar is much bigger than P min, some bad places are still going to be in outage, right? For example, basements or elevators, places like this. There's nothing we can do about those places. No matter how big we make PT and PR bar on the boundary of the circle, some places inside the circle just going to be out of coverage anyway. Okay. So the same outage, and let's not confuse the two concepts, right? The other one was P out. This is P out cell. I'm just respecting the notation of the textbook so that you don't get confused. That one was a function of the distance. This one is not. This is over the whole cell. So the cell outage is the average number of percent of locations in the cell where the received power is below the sensitivity P min. Okay, that's the cell outage. And the cell coverage is the complementary. It's 1 minus the 1 minus the cell outage. For example, if the cell outage is 1%, the cell coverage will be 99% and so on. Okay? So let's try to calculate this P out cell. All right? And this involves a little bit of math, so I'll take you through it and ask questions if you have any doubts. So the way we're going to compute this, and let me put up a picture that's going to help us. Okay, so this is from the textbook. It's picture 2.10. So this is our circle. If we had an ideal cell, now we have these irregular shapes, right? So let's break up the circle into little tiny areas, differential areas. Here's one such area, and each is at a distance r from the center. So we have the transmitter in the center, the base station. Okay, we have a circle of radius capital R, and we break it up into tiny little pieces, this sub A, differential areas. At distance is R. Okay, so retain this picture. And now we're going to integrate over the whole circle. That's the integral up here. We're going to integrate over all these tiny little areas a function which I'm indicating with a 1, which is called the indicator function. So this function is a very simple function. It takes two values. It takes the value 1 or 0, depending on whether the argument in brackets is true or not. So if the argument in the brackets is true, the function takes the value 1. If it's not true, it takes the value 0. Okay, so that's why it's called the indicator function. It indicates if this statement in brackets is true or not. Okay, so the statement in brackets says that the received power at this point, the A, which is at distance r, is less than P min. Okay, So we're going to integrate over all the cell, all these little areas in the circle, and we're going to count 1 on those that are in outage, right? Those where the power is less than P min. And we're going to count 0 on those that are not in outage, okay? And then we're going to divide by the area of the cell. Just to simplify things, we'll just take a circle. So it's pi r squared. And that's going to give us the fraction of locations in the cell that are in outage. Okay? Now that actually is a random quantity because of shadow fading. So the shadow fading, we don't know what it's going to be. We only know its standard deviation, but it's random. So at the outside, we're going to take an expectation to compute the average number of locations. Okay? So inside the expectation, we have the number of locations that are in outage, and then we expect it. We get the average number of locations that are in outage. Okay? So now we'll go through the math, but is that clear as a construction? Anybody has any doubts? Okay, so let's proceed. And we can go to the second step here and exploit the fact that the expectation is a linear operator, and so is the integration, and so we can swap them, all right? This is a constant, so we can just bring it outside. And we can now bring the expectation inside the integration. So we have just the same constant, same integration. Now the expectation is inside, and everything else is the same, okay? So very easy step. In the first step, we're going to actually evaluate this expectation, okay? And it's actually very easy. So let me take you through it. Okay, so we have this indicator function, which because of shadow fading is a random variable, and as I told you, it takes 2 values, 1 or 0. Right? It takes 1 if this inequality is true. It takes 0 if it's not true. Okay? So how do we compute the expectation of a random variable that takes 2 values? Okay? 1 and 0. So this expectation, I'm not going to write the brackets, but the expectation of this indicator function is equal to 1 times the probability that the variable is 1. So when is the variable 1? When PR is less than P min. Okay? So this is probability. It's very unfortunate that probability and receive power have similar notational terms, so be careful. So capital P is power, little p is probability. Okay? Okay, so 1 times the probability that we have a 1 plus 0 times the probability that we have a 0. Okay, which is the probability that the received power is bigger than P min. Okay? Everybody understands this formulation of probability? Okay. Now, luckily for us, this is 0 times something is always 0, and 1 times something is always 1, right? So we're left with this guy here. And this, remember, is exactly what we defined 2 slides ago as the outage probability at a distance r. Okay? This is by definition the outage probability. So this whole expectation turns out to be the outage given P min at a distance r. Okay? Yes? Are you? Yeah. I just realized that that doesn't help. So I'm just trying to use the same notation that is in the book so that we don't get messed up with different notations. But it is a very unfortunate choice of terms. Although I have to say they are pretty standard too. So usually little p's are probabilities and big p's are powers. So just be careful. Any other questions, or you guys still with me? Okay, so we're here. Okay, now we're gonna go over here. So now we're gonna try to integrate this, right? So integrate over the cell. Remember, for simplicity, we just have a circle here. So this is an area integral. So its integration from 0 to 2 pi in angle and from 0 to r in distance, okay, of our function times the area of, so each of these tiny little pieces of area has an area given by r dr d theta, okay? This is complex integration. I'm sure that you've seen it before. And so we can just work out a little bit. Good thing for us is that the function that we're integrating over does not depend on angle. It depends only on r. So we can just immediately integrate over angle, and we get 2 pi. So we integrate from 0 to 2 pi this differential of angle, and we get 2 pi. Okay? So that gives us 2 divided by pi r squared. And I might have an extra pi here. Right? I think this pi shouldn't be here. So apologize. So correct this. And we still have the integration over r of, and now p out, remember, we just saw is 1 minus q of all this stuff. So this is the intercept, gamma, and now it's r over d0. And that's the end of it. That's how far we can go. Okay? Now, there is a footnote here, which is that you may or not remember that the model we're using, so let me write it again. This model we're using for the path loss, which is that PR divided by PT equals K times d0 over d per gamma. We're using this model for the path loss. This model is only bounded when d is bigger than d0. Okay? So that means that there's actually a little circle here for distances smaller than d0 where the model doesn't really work, right? So there's a little ring of exclusion here where we're integrating a function that's actually not exactly how things behave. But this ring is pretty small, and so most of the area is outside the ring, so it's a very good approximation. But nonetheless, let's note that for completeness. So this has a small perturbation effect we're going to neglect. So this is a pretty nasty integral, and as it turns out, actually it can be solved. And the answer is in the textbook. This integration is beyond this course, so don't worry about the details. You don't have to know how to integrate this. But it is a useful result anyway. So it's fairly messy. It's given as a function of these two parameters a and b. So the integration itself is a function of q functions. And there are these two parameters that make the expression a little simpler, more compact. Nonetheless, it's pretty involved. But it is very useful. So we'll go through an example here, right? So let's say we have a cell with a capital R being 600 meters, typical value. We have a transmit power is 100 milliwatts, and the sensitivity is minus 110 dBm. Let's use a 3.71 gamma, which is Fermi standard. As I told you, values between 3.5 and 4.5 are typical. The intercept is minus 31.54 dB, which is used in many of the examples, at 1 meter. And the shadow fading has a 3.65 dB deviation. So you plug all these numbers in this formula, and you get that the outage over the cell is, I guess, 41%. And so the coverage, which is 1 minus the outage, is 59%. Okay? So this is a pretty bad coverage, right? Less than 60% of the cell is covered. So this is completely unacceptable. Lots of unhappy customers. Now notice that if we relax the sensitivity, so if we have a phone that is 20 dB better, 10 dB better, right? So you can pick up a signal that's 10 dB weaker. We jump from 59% to almost 99% coverage. So you can see that 10 dB in sensitivity make a huge difference, right? So in other words, another way to read this, a lousy phone with this sensitivity will work in 59% of the places. A better phone with 10 dB better sensitivity will work in 99% of the places. So you can see how big a difference it makes, the 2 dB in phone sensitivity in terms of coverage. Yes? Yes, that's exactly right. If you increase PT by 10 dBm, in this case, because there's no interference. So the question was that if we increase PT by 10 dB, we'll get the same result, and the answer is yes. Now, the problem is that the amplifiers can only supply so much power. In fact, the amplifier is the most expensive part of the base station. So it's always good to keep the transmit power as low as possible because of cost. So, but you're right. And theoretically, increasing the sensitivity is equivalent to increasing the transmit power and vice versa. Yes. Good point. Yes, sir. Yes. Yes. So we're saying that we can operate with 10 dB less signal to noise ratio. That's exactly right. Yeah. So a better phone will have a better sensitivity. It means that it can operate with less signal to noise ratio. That's exactly right. Other questions? The answer, the question, I'm repeating the question for the CBN students. They've been complaining that they don't hear you guys. So the question is, isn't 100 milliwatts low for a base station? The answer is yes, very low. This is actually typically what a phone will transmit. So a base station will typically transmit about 30 watts, even more. Yeah, so you could see this, for example, as a Wi-Fi example, more than as a cellular phone example. So the numbers of scale, essentially, I think Professor Goldschmidt was trying to find numbers to illustrate the point that 10 dB can make a huge difference in coverage. So I think he just tuned the numbers so that they came out nice. But you're right. It would be a very low power for a base station, indeed. Okay. Other questions? Because that's it. We're done with this. This is chapter 2 in the textbook. So that's the end of the chapter. Any more questions? Okay, so let me just summarize what we saw. We saw that the presence of shadow fading leads to outages and irregular cell shapes. Okay, and we saw that the cell outage dictates the average percentage of locations in the cell that are in outage or not in outage. The coverage is exactly the complement of the outage. And then we saw how to compute it, and we derived a useful formula to compute it. And with that, we'll wrap this up. And we'll start with some new material, and then we'll take a break in about 20 minutes. So this, what was supposed to be lecture 3, corresponds with the chapter 3 in the textbook. Okay. So this is the outline. We're going to talk about signal representation, bandpass and low-pass representation. Some of you may have seen this before, but it's something that we'll be using throughout. Then we'll have a little review on stochastic processes. Remember, last time we went through a review on random variables. So today we'll talk about stochastic processes. And then we'll start with the small-scale propagation. So we'll talk about multipath model, Doppler spread, coherence time, delay spread. And then we'll talk about narrowband channels first, and then wideband channels. So we'll compute the mean and the autocorrelation of a narrowband channel. We'll compute its power spectral density. We'll introduce something called the Clark-Jakes uniform scattering environment, which is a very useful tool. And then we'll talk a bit about the amplitude and power distributions. Rayleigh, Ricean, and Nakagami are the most standard ones. And then I don't think we'll get there today, but we'll talk about wideband channels, power delay profiles, and coherence bandwidth, and just a little bit about depolarization. Okay, so we already saw this. A couple of announcements. So the location for the TA office hours have changed. So they're now going to be taking place on the 8th floor launch of the Shapiro building. Okay, the times are the same, right? Okay. And you guys please remind me, if you ask me a question, remind me to repeat the question so that the CBN students can hear it. Sometimes I forget, so I appreciate that. Okay, so let's go over this part before the break at least. Signal representation. Okay, let me clear the board first. Okay, communication typically takes place within a bandwidth B or 2B around some center frequency FC as per spectrum regulation. Remember we talked about this in the first lecture. So, for example, for cellular systems, FC is about 2 gigahertz typically, and 2B will be typically on the order of a few megahertz. Okay? So, a passband signal that is centered on this frequency FC can be expressed as something times a cosine at this frequency. Okay? Remember from basic signals and systems that the way to center a signal at some frequency is to multiply it by a cosine of that frequency. Okay? So that centers a signal that has zero frequency. That moves it up to frequency FC. Okay? Now, most of the processing takes place at baseband, which is before the conversion to FC. So typically, most of the operations in the transmitter take place at baseband, so at zero frequency. And then just before the antenna and the amplifier, they're up converted to FC by something like this, by multiplication by a cosine, which is the modulation. We bring it up in frequency, we amplify it, and we send it out on the antenna. And then at the receiver, the opposite process takes place. So the signal comes through the antenna, is amplified first, and then it's down converted from FC down to baseband, which is zero frequency. And then the processing takes place at baseband with all the demodulations and decoding and all the details. Okay? So the first stage is pretty much the down conversion and an amplification. So it is often convenient to work with the baseband signal instead of with the whole signal that has the frequency built in. Okay, so we're going to be doing a lot of that. And now in this particular section, we'll see how to represent signals or how to transform signals from the passband domain onto the baseband domain. So from the FC vicinity to the zero frequency vicinity. Now first let me point out that if we have a frequency of that form, right, some signal times a cosine of frequency FC, we can actually superimpose a second signal of the form another signal, whatever you want to call it, times the sine of the same frequency. And we can superimpose these two signals, one on top of another, and without interference between them, in the sense that we can actually separate them perfectly and tell one from the other. So I don't know if this is evident to you, so I'll give you some arguments as to why this is true. These two signals are orthogonal. So what that means is that, for example, if we multiply these two signals and we integrate over time, we get 0, right? Because the sine and the cosine multiply and integrate it gives us a 0. Another way to see it is that these are two vectors that are orthogonal. So I'll get into that a little more in a couple of slides. So for now, let's just keep the notion that these two signals are orthogonal, and so they don't see each other. They can actually coexist at the same time on top of one another. So what this reflects is the fact that the signaling space we have around this frequency has two dimensions. One is the cosine dimension, one is the sine dimension. And these are usually called in-phase and quadrature dimensions. So typically the cosine signal is called the in-phase signal, and the quadrature signal is called, the sine signal is called the quadrature signal. And these are orthogonal. So let's put them together. So we move the signal called S of t, S of time, which is at the superposition of the in-phase and the quadrature. So it's S sub I of t, which is completely generic function, times the cosine of frequency fc minus, and the minus is arbitrary, just for convenience, it could be a plus, sq, which is another signal, times a sine of frequency fc. Okay? Now, with a little bit of algebra, we can express the summation as in the second quantity here. Okay? So this r indicates the real part, and that's the complex exponential. So I suppose that's pretty obvious to you, but just in case, remind you that e to the j 2 pi xct is equal to the cosine okay, so that's the complex exponential. We multiply this by the s of t at the top. We take only the real parts. We get exactly what we had at the top. So let's go over it. So multiply these times si of t plus j sq of t. So we multiply these two guys. We take only the real part. So we get this one times this one. We keep these ones. Okay. Now the cross terms disappear because they're imaginary. And so we get to keep this guy. Right? J times j is minus 1. And then sq times sine. Okay. So the real part of that product is exactly s of t at the top. Okay. Is that clear, or anybody see that? Okay. Now let's call this si of t plus j sq of t. It's a complex number. Let's call it u of t. We just define it as u of t. Okay. So what we have now is that for a passband signal s of t, a frequency fc up there, with each in phase and quadrature components, can be represented as a real part of u of t times e to the j 2 pi fct. Okay? And u of t we're going to call the low pass or baseband equivalent signal of st. Okay? So these two signals are the same. One is in the passband domain around fc, that's s. The other one, u of t, is in the baseband domain on low pass around 0. Okay, so there's a shifty version of each other. One lives around fc, the other one lives around 0. So in frequency, right, this is 0. We have some signal u of t, right? So this is the baseband equivalent, and the passband equivalent is over here. The same exact signal centered at frequency fc. And they relate in this way. So often we'll find it more convenient to work with u of t, the baseband signal, because we don't have to deal with all the frequencies. But we'll often go from one to another, from the low pass to the passband domain and stuff. U of t is also termed sometimes the complex envelope of S. And we can express it in two different ways. So one is real plus imaginary part. So U of t is a complex signal. So we can express it as real, which is the in phase, plus imaginary, which is the quadrature. Or we can express it in polar coordinates, amplitude and phase. Okay? So A of t will be the amplitude, and phi of t will be the phase. Okay? So that's another way of, a complex number can be expressed in polar coordinates or in real plus imaginary coordinates. And they relate in this way, right? The amplitude is just the square root of the sum of the squares of the in phase and the quadrature. And the phase is the arctangent of the imaginary part, which is the quadrature, divided by the real part, which is the in phase. Okay? And in fact, we have yet another way to represent this. Which is not in the slides or in the book, but let's go over it. So if we put here the representation in polar coordinates, right? So we have the real part. We have the real part of A of t, and t to the j pi of t times okay. So we just plug the polar representation into this equation, and we can expand this very easily. This is just a cosine. Right, so this is just A of t times the cosine of 2 pi fct plus pi. Okay? So this is yet another way of expressing it. It's the amplitude times the cosine of frequency of c and phase pi. Okay? So this is yet another way of expressing s of t. So this is s of t. This is exactly equivalent to the cosine plus the sine on the top. The fact that the baseband signal u of t is complex is a mathematical artifact. Of course, the real signal s of t is always real, and the in-phase and the quadrature components are represented by real and imaginary parts of a baseband signal. So keep that in mind. And another footnote here is that the powers of the in-phase, of the passband and the low-pass signals are not equal, actually. One is twice the other. And you can see that because the power of a cosine is 1/2, the power of a sine is 1/2. So if you work out the powers, for example here, or actually it's easier with the cosine and the sine, you'll see that the s of t has half the power of u of t. And so as a reason, some textbooks, for example, the Series 1 textbook, defines the equivalence in this way. There is a factor of 2 outside, which exactly counters for these differences. And Professor Goldsmith doesn't have the factor of 2, so we're gonna do without. And then I think she manually introduces factors of 2 throughout the textbook sometimes to account for this. So we'll try to keep a tab on those. Okay, so we'll be using this a lot. So I hope you guys will get comfortable moving between the passband domain and the all-pass domain. It's pretty easy once you get familiar with it. If you have any doubts, please ask. Don't hesitate. Okay, because it's a very useful tool. So I think this is a good time to take the break because we're going to start with pretty intense section now. So let's take a break for 15 minutes and then we'll reconvene, okay? Okay, so let's continue. We're going to go now over a review of stochastic processes. I'm saying a review because hopefully some of you have seen this before, and for some of you it may be somewhat new. There is an appendix in the textbook that has a part on random variables and then another part on stochastic processes. So I'm going to cover, I would say, a subset of what's in the appendix and just bare bones what we need for the course, no more than that. It's a very deep subject, but these basic notions we do need. So make sure that you familiarize yourself with them. So let's start with the definition. A stochastic process is a random function of time. So you can see it as a random variable that changes with time. So we're going to call it capital X of t, for example. We use capital, remember, uppercase letters to indicate random quantities, and lowercase to indicate the values they take. And the difference with, between a random variable and a random process is that here there is a time dependence. Okay, so each possible organization or outcome is a function of time, and each sample at a point in time, like t sub naught, is a random variable. So let's try to use a picture. Okay, so this could be two possible organizations of a random process. So one of the two is going to take place. We don't know which one. So randomly, one of the two, actually there may be many others, it's going to take place, and it'll be a function of time. Okay, if we take a point in time, so this is time on the horizontal axis here. If we take a point in time, for example here, the values taken by all these possible organizations are going to give us a random variable. Okay, so possible outcome is a function of time. All the possible outcomes at a given time are a random variable. And for a different time, we'll have a different random variable. Okay, that's the definition. Now, there is a very important notion in random processes, which is stationarity. So a random process is stationary in the strict sense if time shifts do not affect its distribution. Okay, so mathematically, how can we write this? Well, imagine we sample the random process at a number of times, t0, t1, t2, up to tn. Okay, so the probability that the value of the random process at t0 is equal to x sub 0, the value at t1 is equal to x sub 1, etc. If this value is unaffected by a shift of all the times by capital T, okay, if the shifting of all the times by capital T does not affect the outcomes, then we say that this process is stationary in the strict sense, or strict sense stationary. Okay, that's it. So if we shift everything by some arbitrary time, capital T, the probabilities don't change. That's what the stationarity entails. Okay? Very important notion. Another notion, and we saw these for random variables, is independence. Remember that for random variables x and y, independence means that the joint distribution of x and y is equal to the product of their marginal distributions. Okay? So a similar concept applies with processes. So if x of t and y of t are independent processes, then we can write that the probability that x at t0 is equal to x0, etc., x at t1 is equal to t1, etc., while y of t0 prime is equal to y0, and blah, 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 y of tn prime is equal to yn, the probability that all this takes place is equal to the product of the probabilities that the x's takes their values and the y's take their values. So if we can factor the joint probabilities into a product of the probability of all the x occurrences and all the y occurrences, then x and y are independent. So it's a generalization of the notion of independence in the random variable, except that now it entails samples taken at a point in time. And for this to be true, and also for this to be true, it has to hold for any choices of these times. Okay, so for any set of times we pick, this has to be true for the process to be stationary. And for the process to be independent, this has to be true for any set of times we may choose, of all the possible times that exist. Any questions here? Stationarity, independence, clear so far? Okay, good. Remember that the mean of a random variable was denoted by mu. So the mean of a random process is mu of t. So it is a function of time, and it's just the expected value of x of t. So at each time, we have a different expectation in general. Okay? We also have an autocorrelation. Remember that we had also autocorrelations for random variables. So the autocorrelation of a random process x measures the correlation of samples taken at different times. Okay, so we'll denote it by a sub x, and it's a function of t and delta t. So a sub x is the expected value of x of t times x of t plus delta t. And the star here is a conjugation, so if x is complex, we have to conjugate it. If it's real, then that is not necessary. Right? So we take the function at time t and the function at time t plus delta t, multiply them and expect them, and that's the correlation that's the correlation at t delta t. Okay? Now, if the process x is stationary in the strict sense, then what we have is that the mean is a constant. It's not a function of time. And this is quite obvious, right? We said that for a process to be stationary, it has to be invariant to a time shift, right? That means that the mean has to be the same if we shift it in time. So it means that it cannot depend on time, right? It has to be constant, because otherwise it will change if we shift it. So it has to be constant necessarily. So if a process is stationary in the strict sense, then its mean is a constant. And also its autocorrelation does not depend on t. It depends only on delta t. So we can just write a sub x of delta t. So it's the same for every value of t. So in other words, if the process is stationary, then because time shifts don't matter, the correlation depends only on the relative difference between the 2 points, relative time, but not the absolute. So as long as the relative difference is the same, doesn't matter where we choose them. So if we take 2 points spaced by, I don't know, 10 seconds, doesn't matter where we start. As long as they're separated by 10 seconds, doesn't matter which points they are. Okay? So then we don't need to put t, we just put delta t. Okay? So if a process is stationary in the strict sense, then it has these two, it follows these two conditions. It's the mean is constant, and the autocorrelation only depends on delta t. Now, there are processes that satisfy these two conditions, but are not stationary in the strict sense. So those are called stationary in the white sense. So it's a less strong condition. It's a milder condition. Okay. So white sense stationary means that the mean is constant. The correlation depends only on the relative times, and yet the process may not be strict sense stationary. Okay. So in other words, strict sense stationary implies white sense stationary, but white sense stationary does not imply strict sense stationary. So strict sense is stronger, and white sense is weaker. Okay, so white sense has a bigger set of functions, and strict sense has a smaller set of functions. Okay. Now let's say we have two processes, x of t and y of t. We can define their cross correlation, and it's essentially the same definition of the autocorrelation, except that we now use x and y. Okay, so we take x at t, conjugate it if it's complex, times y at t plus delta t, multiply and expect, and that's the cross correlation between x and y at t delta t. Okay. Now, if both processes are white sense stationary, in fact, also if they're strict sense stationary, of course, then the autocorrelation doesn't depend on t, depends on only on delta t. Questions? Clear so far? Okay, good. The power spectral density, let's call it PSD, of a white sense stationary. So now we're going to just restrict ourselves to white sense stationary processes, which most of the time we'll be dealing with these kind of processes. the power spectral density is simply the Fourier transform of its autocorrelation, A sub x, taken with respect to delta t. Okay, so we take A sub x of delta t and take its Fourier transform, and we get a function of frequency, which is S sub x, and that's called the power spectral density. Okay, so we'll be using this as well. And those of you who are not too rusty on Fourier theory, or remember that the power of a signal, which is the expected value of its magnitude square, and which equals, of course, the correlation at 0, right? Remember that the correlation up here, right? If you put delta t equal to 0, you get exactly the power. Okay. So you may remember that you have a Fourier transformation between two domains. The value of the function in one domain at 0 equals the integration of the other frequency in the other domain over the whole support. Okay, so the correlation. So remember, correlation and PSD relate through a Fourier transformation, and by properties of the Fourier transformation, the value of a function in one domain at 0 equals the integration of the function of the other domain, and vice versa. Okay, so the S of x of 0 is the integration of the correlation in the same way. That's the basic property of Fourier transformation. So an easy way to compute the power of a signal of a random process is by integrating its power spectral density, which in fact is why that's called the power spectral density, right? Because it gives us the power at each frequency, and summing over all the frequencies, we get the total power. Okay. Before we get into ergodicity, so are we clear so far? Okay. I guess most of you have seen this before. Okay. Another notion that's extremely important, ergodicity. Okay, so a wide-sense stationary process is called ergodic in the mean if its time average mean equals its probabilistic mean. Okay. Now let's be careful not to confuse these two notions. Right. So let's go to this example here. The time average mean of this particular organization, it's integrating this function over time and dividing by the time. Okay, so computing the average of this function. Probabilistic mean is to take the value at some point in time and take an average over all possible organizations. Okay, so if these two quantities are one and the same, so mathematically, if the limit for t going to infinity of the integration between minus t and plus t of x of t divided by 2t, that's the temporal average. Okay, we integrate over time and divide by the duration, temporal average. If that equals the expected value, then we say that this process is ergodic in the mean. Okay. So maybe I can give you a couple of examples to see if we can illustrate this point. Because it's a bit tricky because most random processes that we can think of are ergodic, but many are not. So I guess the ones that are easy to think about are ergodic, and yet sometimes we're going to find non-ergodic processes. So let's see. Okay, let me give you a couple of examples. Imagine a sequence of coin tosses. Okay, very long sequence. So I toss a coin many times, and every time I get tails or heads. Okay, so time here is a succession of the coin tosses, and each one can take values head or tails. Okay, so the probabilistic mean is the expected value of a single toss randomly, right? And the temporal mean is the average of many tosses. So I take 200 tosses. I count how many tails, how many heads, and then I compute what's the fraction of the time I get tails or heads. So imagine that I have a fair coin. You guys think this is an ergodic process or not? Anybody wants to guess an answer? Is it ergodic? It is ergodic, right? Because if I toss a coin once, I have 50% of chance of getting tails, 50% of getting heads, right? If I toss it 10,000 times, I'm going to have 5,000 tails, and not exactly, but in the limit, going to infinity, I'm going to have exactly half the time tails, half the time heads. Okay. All right, let me give you another example. That's obvious. Let me postulate the following random process. Choose some location in the US, in the United States, randomly, and then look at its temperature over time as a random variable. Right? Temperature over a whole year, for example, for a randomly chosen location in the United States. Is that ergodic? Anybody wants to guess? Completely non-ergodic, right? If I take a probabilistic average, I'm going to get the average temperature in the whole United States over the whole year, which can be, I don't know, 20 degrees maybe. Who knows, right? If I do a temporal average in Alaska or in Miami, I'm going to get very different answers. And every place will have an answer that will be in general different from the average of the whole US. Okay? Yes?
Alaska temperature is very low in Miami, right? We just compute the deviation from their average.
Okay, the question is if we normalize the averages of each location and look at the deviations, would that be ergodic? I think it wouldn't be, but that's, in fact, I'm sure it wouldn't be, although it's a little less obvious, but let me try to justify why it wouldn't, right? I lived for a couple of years in San Diego, California. Wonderful place, by the way. It's fantastic. The temperature is pretty much flat the whole year. It has very little changes, you know. It's always wonderful, between 20 and 25 Celsius. And inside New York City, right, even if we normalize to the same average, it has huge peaks in winter and in summer, right? In summer here, in winter we're freezing, and in summer, it's really hot. So even the deviations are non-ergodic, right? So I hope that helps illustrate a little bit this notion of ergodicity, which is quite important. Now, it's a strong notion because ergodicity entails stationarity, but not vice versa. So it is a very strong notion. Okay. So a couple of final notes. Gaussian processes are the ones that are going to encounter the most. And in the same way that the Gaussian random variable is completely determined by its mean and its autocorrelation, its variance in that case, a Gaussian process is completely determined by its mean and its autocorrelation. Okay? Not only, remember that for Gaussian random variables, actually, well, first let me say, if a Gaussian process is white and stationary, then it is also strict and stationary, which is in general not true, right? So remember, in general, strict sense implies white sense, but not vice versa. Now for Gaussians, they're equivalent. So one implies the other, and vice versa. And in the same way, remember that for two Gaussian random variables, if they're correlated, then they're independent. In the same way, two Gaussian random processes, if they're uncorrelated, then they're independent. Remember that in general, independence is stronger than correlation. So independence means uncorrelation, but not vice versa. But for Gaussians, they're equivalent also. So Gaussian processes are very special, right? For Gaussian processes, white sense and strict sense stationarity become equivalent, and uncorrelation and independence become equivalent, but only for Gaussians. In general, that's not the case. In general, one is stronger than the other, but for Gaussians, these notions are equivalent. Okay? Which is a nice thing because Gaussian processes are the ones we're going to see the most often. And this really makes it much easier to deal with them. Okay, so that's the end of this review. I hope that it helps those of you who haven't seen this for a while. If you have any questions on random processes, otherwise, we'll start with small-scale fading. So this is in correspondence with chapter 3, okay, in the textbook. Okay, let's see how much we can get through today. Remember that we've talked so far about large-scale propagation, path noise and shadow fading, that manifest themselves over fairly large distances. Okay. Now today we'll start talking about small-scale features that manifest themselves over short distances, or on the scale of the wavelength. Now, to facilitate the study of these small-scale features, we'll often regard the channel as what's called locally stationary, which means that we'll assume that the large-scale features remain constant. And we'll study, so we'll assume we're looking at distances that are small enough that the path loss and the shadow fading are not going to change too much, right? For example, we're going to be looking at things that happen over centimeters or inches. And so over these distances, the path loss definitely is not going to change too much. And usually also the shadow fading is not going to change too much. So we'll often regard them as constant as we study the variations that occur because of this small scale propagation. Okay? So this separation enables a clean, this is an approximation, but it enables a clean separation of what's large scale versus what's small scale. So we'll be using that a lot. In theory, one can use ray tracing also to characterize small scale behavior, but it is really hard and very inaccurate. So the common approach here is to use statistical methods. So we'll just exclusively deal with statistics here. And we'll deal with what's called the statistical multipath model, right? So this is a illustration. We have a transmitter sending a signal and a receiver. And the signal is going to bounce around all sorts of obstacles, okay? So we'll have a direct path, possibly, maybe not, the line of sight, ground reflection, and then all sorts of reflections of other obstacles. Typically, the strongest ones are the ones that are in the vicinity of the receiver. The ones that are far are going to contribute less. But they can be there too. So we'll have a random number of what's called multipath components, right? So each one of these reflections is going to be called a multipath component. And each one will have a different amplitude, in general, a different amplitude, different phase, different Doppler shift, which I'm going to introduce in a second, a different delay. The reason being that these paths will not have the same length in general. Some of them are going to be shorter, some longer. So that's going to give rise to different delays. And all of this stuff is going to change with time. Okay? So in essence, what we have is a linear time varying system or impulse response. And maybe I can so we can regard the multipath channel, if you will, as a box, linear time varying. Okay? With an input and an output. So we'll try to study this box. So let's use the same notation. The signal we send is called S of t in the passband domain. And remember that we can express this using the low pass equivalent as the real part of u of t times e to the j 2 pi x c t. Okay? So S of t is the passband signal, and u of t is the equivalent low pass, and fc is the frequency. And I hope you can read this, e to the j 2 pi fct. We take the real part, we get S of t. Okay, so these are equivalent representations. So that's the signal that's being sent out into the channel. And what do we receive? Well, we receive a superposition of all the signals arriving through all these different paths. Okay, so we can write this as a summation, which you have out here. Okay, so let's try to distill this. We have a summation from n equals 0 to n sub t. So capital N is the number of components, so the number of paths. Okay, and it could be a function of time in general, so that's why we have the t dependence. We use the n equals 0 to denote the line of sight component when it's there. So we start the summations at 0 if there is a line of sight, like in this picture there is one. And if there isn't, we'll start at n equals 1, okay, just to make things clear. Each one has an amplitude, each component has an amplitude alpha of t, which relates to path loss and shadow fading, something that we already studied. Each path has a length, d sub n of t, and an associated delay, tau sub n of t. And the delay is equal to the distance or the length divided by the speed of light. So that's the time that it takes for the wave to go to reach the receiver through that path, is the distance divided by the speed of light. Okay? And each path has a phase that's just 2 pi fc times the delay. Okay? So this is a typical relationship between time and phase. Given a frequency fc, The phase is 2 pi fc times the duration. So those are the quantities that are involved. And we have a summation, and little n is a counter. So it goes from 0 to capital N. And each term is one of the multipaths, and it has an amplitude alpha sub n of t. It has a delay tau. Okay, so it's u of t divided by tau. And so whenever we have a t, right, we're going to have a delay, tau sub n. And the tau itself, the delay itself can be a function of time. So the delay itself is a function of t. Okay? So is that clear so far? The first equation. Okay? Each of the terms. So each component has an amplitude, alpha, and a delay tau at this point. Okay? Now, what we can do in the second equation is factor out a term that is common to all the terms in the summation, which is this e to the j 2 pi fct. Okay, that's common to everybody, so we can just take him out. And what we have is a typical low pass to pass band equivalence. Okay, so we have something that's the real part of something times e to the j 2 pi fct. So that's a pass band signal whose low pass equivalent is what we have in the brackets. Okay, so what we have in the brackets, we call it y of t. All right. And one more clarification: I replaced 2 pi fc tau on the top by 5. Okay, so I'm applying this definition here. Going from the first to the second equation, I apply this definition and replace e to the minus j 2 pi fc tau on the top with e to the minus j5. Okay, so I hope I don't lose you there. And as I said, I'm going to call all this stuff in brackets y of t. Okay, so what we have is that at the output of the channel, we have r of t, which is equal to the real part of y of t times e to the j 2 pi fct. Okay, so that's s of t and r of t are the passband signals, and u of t and y of t are the equivalent low pass. Okay, equivalent notations. Okay, so I'm sure that most of you have seen linear systems before. So when you have a linear system, in this case linear time varying system, with an input and an output, they relate via something which is called the impulse response of the system. Okay, so the output is equal to the input convolved with the impulse response. Okay, so we're going to call the impulse response C of tau and t. So the impulse response characterizes the behavior of a linear system, and properly defined, it gives us the observation at the output at the time t. Oh, oops. So C of tau t characterizes the observation at the output at time t when an impulse was injected at the input at time t minus tau. Okay, that's the definition of an impulse response for a time varying system. We're going to call it C. And so the output is the input convolved with the impulse response. So in low pass notation, we have that y of t is equal to u of t convolved with C of tau comma t. Okay, that's the relationship. And we have both of the signals, so we can identify C. Remember, we have y here. Y is all this stuff in brackets as a function of u, and we can just by identification, we can infer that C is equal to this expression here. In other words, if you take this impulse response and you convolve it with u of t, you're going to get exactly this term in brackets. Okay, I don't know if that's very obvious to you. I guess you all know how to convolve with an impulse at some delay, right? If you convolve a signal with an impulse at some delay, it just shifts the signal onto that by that amount. So this impulse convolution with these deltas is going to shift u of t by tau of n. Okay, so that's what we have here, shifted versions. And then all the other stuff is just a multiplying factor. Okay. So this is the impulse response of the channel. And it's just a sum of impulses at each of the delays of each of the multipath components. So maybe we can plot that. So let's try to plot this. It's not easy because it's a function of t of tau and t, but we'll try. So this will look like something like this. So this axis is tau, and this is c. So we have an impulse response, a delta impulse at tau 0, another one at tau 1, another one at tau 2, up to tau n. Okay, so these are these impulses at each of these delays, and now each one is multiplied by an alpha. Sorry, I'm not here, which is a function of time. So the way to visualize this, okay, you cannot really plot this. You have to imagine it as a movie. Okay, so imagine that this is a movie where each of these impulses is oscillating, and alpha of t, it's the amplitude or the size of the impulse. Okay, so imagine that this becomes smaller and larger over time, each of them. Okay, that's alpha of t, the amplitude. The delays can also move over time because taus are a function of t. So these guys can be moving around. They're oscillating amplitude, and they have a phase, and that's now even tough to visualize. You can imagine that they're rotating around, for example, and the phase is the orientation. Okay, so that's about as close as I can get to describing it. Now, things get easier in the special case that the channel is time invariant. So if nothing changes with time, so we can remove all the time dependencies, then we just have a bunch of impulses at fixed positions, fixed amplitudes, and fixed phases. So these would be, these would correspond to a particular time invariant channel. If it's time varying, then you have to imagine the animation on it. Is that clear or not? Are you guys following or not? This part is probably, this chapter is probably the most intense in terms of math. So, you know, slow me down if you have to. Okay, don't be afraid. Okay, I'll continue. What happens in actuality is that rather than having a discrete number of components, as I'm having here, a real channel will have a continuum. So we'll have some level of response at each delay. So instead of being discrete here, we have a continuous function that changes with time. And we're going to stick with the discrete version for now because it's easier to handle. And it's a pretty good approximation as long as you have a sufficiently large number of impulses there. So we'll stick with that. But later on, we'll probably move to the continuous approximation. But for now, we'll keep it discrete. Okay? Okay, so now I'm getting to Doppler spread, but I want to ask you again, so are you guys clear so far with this impulse response? Okay, let's proceed then. Okay, so we have motion, and that results in something called Doppler. And I'm sure most of you know what Doppler is. We've all experienced it, right? When you're in the street and a car is approaching you, it sounds in a particular way. When it's moving away from you, it sounds differently because of Doppler. Okay. So what happens with Doppler is that you're sending a signal of a certain frequency. Imagine you're sending a cosine of a certain frequency, but the receiver or the transmitter or both are moving. What happens is the cosine gets compressed or expanded by the motion, and that changes its frequency. Okay. So if you move towards the receiver, you're going to compress the cosine, and so increase its frequency. If you're moving away, you're going to expand the cosine. Your motion will expand the cosine, and so will reduce the frequency. Okay. So this frequency shifts because of motion, compound into phase differences. That's why this is pretty important. Even if the shifts are small, as they will be in practice, over time they compound over phase differences that are significant. So let's look at one of the paths. Remember, we had all these paths here. Let's look at one of them, okay, which is arriving with a certain angle theta sub n, okay? And the receiver is moving at a speed v with respect to the, so theta sub n is the angle between the wave incidence and the vector of motion, okay? So the length of this path, remember we use d sub n, so we know the length, is equal to some d0, which is fixed. Let's say this is the length at time 0, plus the speed times time, projected onto the path. Okay, so there's a cosine here because you have to project the speed onto the direction of the wave to get the effective speed along that vector. Okay, for example, if the wave is arriving perpendicular to the motion, the length of the path does not change. Okay. On the other hand, if the path is lined up with the motion, it changes very fast. Okay, because you're exactly speeding away from the transmitter, so the increase in length is maximum. If it's perpendicular, it's not going to change. That's what this cosine is doing for us. Okay, so this is just space equals speed times time, nothing else. Now the delay associated with this length is just the length divided by the speed of light. Okay, we saw this before. So time is equal to distance divided by speed. And the phase that is associated with this delay is 2 pi fc times the delay. Okay, so now we plug here the fact that the delay is equal to this d0 plus v cosine of theta n here. So we plug this in here, and we get a fixed term, a fixed phase, which is 2 pi fc d0 divided by c. So this is fixed. And something that changes with time, which is 2 pi fc v, which is the speed of the vehicle, divided by c, times the cosine of the angle, times t. Okay? So this phase is constant. This phase changes with time. Now, the frequency is the derivative of the phase. So we can compute frequencies by taking the derivative of the phase divided by 2 pi. So the Doppler, which is the change in phase over time, is this term, right? The derivative of a constant is 0. So this plays no role in the Doppler. And the Doppler is the derivative of this with respect to t. So t goes away. And we get, we take the derivative divided by 2 pi, so the 2 pi goes away, and we get that the Doppler on this multipath component, the nth component, is equal to v divided by c times fc times cosine of theta n. Okay? So the Doppler frequency, in other words, if we send the cosine of frequency f sub c, we'll receive a cosine of frequency f sub c plus fdn, where fdn is the speed of the vehicle divided by the speed of light times fc times the cosine between the angle of incidence and the direction of motion. Okay? Is that clear? Questions? Yeah. Yes, that's a very good point. So in the next slide, we'll get to some numbers. So the question was, typically the speeds v are going to be very small compared with c, right? Now fc is also very large. So we'll see now some examples, but it's a very good question, right? How large are these Dopplers? They are very small, but it's still important. So let me defer the question until the next slide, but it's a very good point. So notice that if theta n is 90 degrees, then the cosine is 0, and there is no Doppler, which is intuitive, right? So if you're moving exactly perpendicular to the incidence, there is no compression of the frequency, because you don't move away from it or into it. And the compression is maximum if theta is 0 or pi. So if you move into the signal or away from the signal, there's a maximum shift in frequency. Okay, so that seems to make sense. Okay, it's a good sanity check. So, on to your point, and first let me define what's called the maximum Doppler frequency. So, what's the maximum value of this Doppler frequency? Well, the cosine cannot be bigger than 1, so the maximum value is just this factor. Okay, so that's called the Doppler spread. So, and it's a very useful quantity, which is speed of motion divided by the speed of light times the frequency of the signal. That's the Doppler spread. And now let's exemplify. Okay, so at pedestrian speeds, 6 kilometers per hour, and actually that's pretty fast walking, in fact. And 2 gigahertz, typical value, we get that the Doppler shift is 10 hertz. So you are right? You're sending a signal of 2 gigahertz, and it's only shifted by 10 hertz. It appears to be insignificant, right? At 100 kilometers per hour, so vehicular speed, same frequency, 2 gigahertz, the Doppler spread is 185 hertz. So it's still pretty small, right? So this appears to be negligible, but it has a very important role, which is the following. The reciprocal of the Doppler spread roughly gives the coherence time of the channel, which is the channel, the time that the channel needs to change significantly. In other words, the channel is going to change over time, and for how long it's going to stay pretty much constant before it changes? Roughly is 1 over FD. So let's now look at these examples, right? Walking speed, 10 hertz. How much is 1 over 10 hertz? Anybody? 100 milliseconds. Okay, so if you're walking, the channel will stay more or less constant for about 100 milliseconds. And that's true, that's the case. If you're in a car, you'll stay constant for about 5 milliseconds. And that's also true. So one has to design the system for these type of times. In other words, there's a lot of processing in the phone to account for these fast variations. So we'll get into that a little more later today or next week. So this is a very important quantity. The coherence time, which is roughly the reciprocal of the Doppler spread, tells us for how long the channel stays pretty much constant before it's going to change. Okay? And that allows us to classify the channels into 2 classes. Fast fading and slow fading, depending on whether the coherence time is bigger or smaller than something called the coding block length, which we haven't introduced yet. But the point here is that we're going to be sending data encoded into blocks. Okay? So if the coherence time is much shorter than these blocks, then we have a fast fading channel. If the coherence time is longer than these blocks, then we'll have a slow fading channel. And these are all idealizations because usually you're somewhere in between. But in terms of analysis, usually one classifies channels into fast or slow and tries to tackle them using different tools. So we'll see more of that later. Okay, so that's Doppler spread and coherence time. And now, if there are no questions, we'll introduce a new notion, which is the delay spread. Okay, so let's look at 2 of the components, which means 2 of the different paths over which the signal propagates. The components are said to be resolvable if the delay differences are on the order of or higher than the reciprocal of the signal bandwidth, 1 over b. So say components 1 and 2, if the tau 1 minus tau 2 is at least as large as 1 over b or bigger than 1 over b, then we say these components are resolvable. Now, why is 1 over b the threshold? I'll show you that in like 5 minutes, so take a leap of faith for now. If that's not the case, if the delays are small compared with 1 over b, then these 2 components, u of t1 and u of t2, or u of t minus t1 and t minus tau 2, are said to be non-resolvable. And so they're going to combine into a single component, okay? Whose amplitude and phase will undergo fast variation. So let me defer that. The point I want to make here in this slide is to introduce the notion of the delay spread, which is roughly the difference between the first and the last arrival. Okay, so let's go back to our general picture. The first arrival would always be, if it's present, the line of sight, okay, because it's the shortest path, the straight line. So if there is a line of sight, that signal will get there the first. Now, there's going to be some distant reflection that will be the last one to arrive. So the difference between these two delays, roughly speaking, and I say roughly because we'll give a precise definition a little later, but roughly speaking, this difference is the delay spread. Okay, so it gives us a notion of how much temporal dispersion there is. So we send the signal at one time, and it gets there at multiple times. So how dispersed are these times? Well, that's what the delay spread quantifies. So what are typical values for delay spread? Well, indoors, like for example, imagine a room like this, reflections take place in walls that are pretty close, 2 meters, 5 meters, 10 meters. So the times are very short. Typically, the delay spreads are on the order of 150 nanoseconds, in that range. Outdoors, the reflections will take place in buildings or maybe small hills that are around or all sorts of objects that are more far away. And so the delays are going to be larger. And so the delay spread in a city will be typically on the order of a microsecond. On like a suburban area or rural area will be maybe 5 to 10 microseconds on that range. Okay? Now, in the same way that we classify systems as fast fading and slow fading, depending on how 1 over b relates to the the block length relates to the coherence time, there's a similar classification has to do with the delay spread. So if the delay spread is much smaller than 1 over b, so we have, as we saw there, non-resolvable components, then we'll say that the channel is narrow one. Okay? And we'll see why these names are chosen. And if the delay spread is bigger, or at least as comparable to 1 over b, we'll say that the channel is wideband. And we'll study these two classes of channels separately now. So let's start with the narrowband channels. Let's see if we can get through it today. And now let me justify to you why the classification between narrowband and wideband is determined by 1 over b. So when we're going to communicate in the next chapters, we're going to talk about coding and modulation. We'll see that digital systems communicate by using pulses. They send sequences of pulses modulated with information. And each of the pulses has a duration t sub s, symbol time, which is roughly 1 over b. Okay? And again, we can point to Fourier properties to justify these relationships, right? So take a signal and its Fourier transformation. The duration of a signal in one domain is roughly the reciprocal of the duration in the other domain. Okay? So if a signal has a duration on the order of t, its Fourier transformation will have roughly a size of 1 over t. Okay? Roughly. So that's why 1 over b is roughly the duration of the symbol. And so 1 over b, so we're going to use 1 over b and t as equivalent quantities here. Even they're roughly equivalent, they're not identical, but we'll use them as similarly. So take this sequence of pulses here, okay? One pulse, another pulse, another pulse. Each of them is ts seconds long. Now take another, so that could be the signal that goes to one of the multipaths, okay? For example, the nth multipath. Now take the signal that goes to another multipath, the mth multipath, which is slightly shifted because the delays are different, okay? So it's the same signal, but it arrived a little later, all right? Because Tm was bigger than Tn. And this is the difference, Tm minus Tm. If this difference is small, right, these two signals are pretty much going to line up. So if we add them up, we'll get something that has the same shape. except there's going to be a little bit of perturbation in the edges, okay, here in the transitions. But by and large, if we add these two signals, we'll get something that has the same shape, okay, except for a little bit of distortion in the transitions. As long as this difference in the noise is small, okay, if this difference in the noise is large, we combine the signals, we'll get something that has nothing to do with either of them. But if the delays are very similar, the summation of the signals will give us a signal with about the same shape. Okay? So that's the definition of a narrow one channel. One where all the delays are close to each other. And so the summation of all of them, of the signal that goes to all these paths, gives us a signal that has about the same shape. Okay? So there's nil distortion. So that's the narrow one channel. And as I said, this duration happens to be about 1 over b. That's why that's pretty much a threshold that determines if the channel is a narrow one or wide one. Okay? Is this clear? Is this clear or not?
Okay, so it has to be much more smaller than CF, right?
Right.
But if you're getting signals at different times, like putting that, if you have multiple, you gotta add up to something that doesn't have the same shape. If each one's a little bit over, it's gonna change the output of the whole signal.
Yeah. So the point is that all of them have to fall within a certain window, right? So let's say the difference between, so take it this way, right? These two are the extremes, the first and the last. Okay? So all the other ones fall in the middle. So that's a more precise way of putting it. So the more precise way is that the difference between the first and the last has to be small. You're right. If I say the difference between any of two has to be small, but the addition of this can be very large. So we could be in a non-narrow one situation. So a precise way to say it is that the difference between the first and the last, which are the extremes, has to be small relative to TS. Okay, good point. So as long as that condition is satisfied, we'll have minimal distortion or acceptable distortion. And we can say that the channel is narrow one. Okay? So mathematically, we can say that U of T minus tau sub n is about the same as U of T minus tau sub m, where n and m are the two extreme delays. Okay? That's the condition we need. Now, let's apply this condition. So let's assume that this is the case. Then let's go back to our signal, the received signal. Remember, this is the passband version. This is the low-pass version. Okay, usual relationship. And we found this before, remember? Right here. So the term in bracket is y. So now we said we are in a narrow one situation where all these delays are very similar. So we can say that this u of t minus tau sub n is about the same for every n. Okay? So we can take this term and factor it out to the summation and take it as a constant, since we're going to neglect these middle changes in delays. We're going to take this u and take him out to the summation. Okay? So that's what I'm doing here. I took this u after the summation, and now I'm just saying, okay, all the delays are similar, so I'm going to call them all of them t sub 0. Okay? So I'm saying all the delays are about t sub 0. So I take this guy out because it doesn't depend on n anymore, and this is the rest of the expression for y. Okay? I'm just taking this out of the summation. That's all. I'm saying that all the t sub n's are about the same as t sub 0, and I'm left with this. So what I'm left with is that the received signal, y of t, is now equal to the transmit signal, u of t, shifted or delayed by t sub 0, and multiplied by this factor here, which is just a complex number, right? This is a summation of weighted exponentials, so this is just a complex number. So the effect of an narrow one channel is a delay and a multiplication by this coefficient, which is a function of time, of course, because everything here depends on time. So an equivalent way to see this is looking at C, the impulse response. And again, we can just take the expression we have for the impulse response here. Remember? That's C. Now we say, okay, so in fact, let me go to the picture, see if I can help out. So when the channel is narrow band, what we're saying is that all these impulses here are very close to each other. Okay? So relative to T sub s, all these guys are very close, and so we're just gonna add them up and represent them as a single impulse. Okay? So I'm gonna take all this summation and say, okay, all these impulses are very similar, all these taus are very similar. Just gonna put one impulse at tau sub 0 and take him out of the summation. And that's here, right? So I take this guy out of the summation and I have the same coefficient times a delay of tau sub 0. These are equivalent expressions. Okay? So this is a delay, and this is a multiplication by coefficient. Same thing over there. Yes? Go ahead.
The impulse comes to function. The impulse comes to function when you do a delay function to that child.
Yeah, what I'm saying is that if you convolve these with u of t, you get that, right? So there are two ways of looking at the same. So I'm making the same approximation in two different ways. Okay, so this is just a convolution of this with u of t. Okay, okay, so now we're going to call this coefficient in summation, in brackets here, the summation. We're going to call this guy h of t. Okay, so the sum of alpha n of t times e to the minus j phi n of t. We'll call this h of t. Okay. So we found that an narrow band channel does not introduce significant distortion in the shape of the signal. So there's not too much temporal spreading because the delays are very similar. That's why. The main effect is a single delay on the whole signal, which is quite irrelevant. And the really important effect is a time-varying scale factor, which is this h of t. So the signal is multiplied, is delayed by t sub 0, and multiplied by h of t, which is a time-varying function. Actually, it's a random process. Okay? So this is really important. So this is called multipath fading. These variations, this multiplication by h of t, is called multipath fading because this is going to change very fast over time and over distance. So this is one of the most important phenomena in wireless communications, multipath fading. And okay, let me defer a little bit of more explanation to the next slide because we have a teacher coming. But recall that this is the definition for h of t, the summation. Actually, it's up here too. And now let's expand this complex exponential into a cosine minus j times the sine. Okay, I'm just doing that. And by doing it, now I have something real and something real. So I have a complex number, or I can define this as the in-phase component of h, and this is the quadrature component. Okay, I'm just expanding the complex exponential into real and imaginary parts. And so I can say that h of t is equal to some real part plus j imaginary part. I'm going to call the real part the in-phase, and the imaginary part the quadrature component. So I'm just using the usual notation. And I'm going to anticipate something that we'll see later in more detail, which is that for large n, and as long as the alphas and phis are stationary, remember that we talked about the center limit theorem last time. So when you sum a number of random variables, you get something that is Gaussian. If you add many of them, you get something that's Gaussian, remember? You have the same with random processes. If you add random processes, a large number of random processes, you get a Gaussian random process. So if we have a large number of reflections in the channel, we'll get that the in-phase and the quadrature components of this fading coefficient are going to be about Gaussian random processes. Okay, and so we'll study them by means of their mean and correlations. And if these are Gaussian, then the amplitude is going to be Rayleigh. So this is the property of Gaussian processes. So if you have two random variables and you look at the amplitude, actually, let me be more precise. If you have a complex Gaussian random variable, so the real and the imaginary parts are Gaussian, the amplitude has a distribution called Rayleigh. Okay, so we'll see that in more detail. You may know that or not. It doesn't matter. But let's look at a picture here, which hopefully will help. Remember these three levels of classification in terms of large scale versus small scale. Remember we had path loss in green, oh, yeah, in green, which changes very slowly with distance and it's always decaying. Then we had on top of that, we had the shadow fading, which is shown in red, which is random, so it can go up and down, and it's slower. And then on top of that, we have now this multipath fading shown in blue, okay, which is this H coefficient. Okay, that's the multipath fading, which is much faster even. So this is going to change on the order of centimeters. So shadow fading changes on the order of meters, tens of meters. Now we have something that changes on the order of centimeters. So this is a picture of a typical fading process with Gaussian in-phase and Gaussian quadrature components. And let me see. Oops. So we have here a distance of a few meters over which the shadow fading is about constant. You see the red line is the shadow fading, so it's about constant. And on top of it, we have this, this huge range of variation of the rarely fading, the multipath fading. And this is one of the biggest problems in wireless communication. I mean, a big part of the processing in your cell phones has to do with this stuff. So its objective is to mitigate these huge variations. This is in dB, right? So you can have 10, 20 dBs of change in centimeters because of this multipath. And this is hugely problematic for communication. It's a terrible channel. Many of you may have experienced multipath fading, like, for example, on FM radios. If you're driving in your car, for example, if you stop at a light, sometimes you stop at a spot where the signal actually has died off. It's very bad. If you let the car move 2 centimeters, so you may be down here, for example, maybe in a bad spot. If you let the car move just a few centimeters, you'll see how the signal recovers immediately. Okay, so that's how you can experience when you drive slowly, rarely fading. Or for example, if you drive in the highway under the bridge, there's going to be a point exactly where the signal that reflects in the bridge is going to cancel the direct signal. You don't get a huge dip in signal. So if you drive under the bridge, you always have a point where the signal dies for a little bit, for a split second, because of multipath. Something that you can, not with cell phones because they have all these mechanisms to protect you, but with FM radios and AM radios, you can experience this by just moving the phone around, the radio around very slowly. You can see how the signal changes. Okay, so okay, I think we'll leave it here because this is a pretty long section now, and there's no point in starting it and just leaving it open. So we'll close it here, and we'll have a second homework posted tomorrow morning, due next week. And that's it. You guys have a good week, and we'll see you next Thursday. Okay?